Hello everyone, welcome back to the channel. I hope you all are doing great. So we were discussing about our previous year questions of the CSIR NET exam, and in that the chapter that we were discussing was the kinetics. So two of the parts of this unit we have already discussed. If you have not watched, playlist is there on the channel, you can check that. I'll provide the link in the description also, even from that you can get the access to it. Okay, so now let us begin with the part number 3. So the first question of this is there on your screens. It says that if the pre-exponential factor in the Arrhenius equation is this much, the value of the rate constant at extremely high temperature it will be close to. So according to the Arrhenius equation, according to our Arrhenius equation, we have the rate expression. Rate constant is equal to A times e raised to the power of minus of Ea upon the RT of it. This is the expression. Now they are saying it is at extremely high temperature, which means we can consider T is approaching to the infinity. So in that case, Ea upon the RT, it will be equal to the 0, right? Because T we have made it to reach to the infinity. So that means rate constant k, it will be equal to A times e raised to the power of 0. So e raised to the power of 0 is unity. That means the pre-exponential factor is equal to the rate constant only. So its value is already given to us, which is 1.6 into 10 raised to the power of 12 a second inverse. This is the rate constant. So k value will be this much. So the answer we are having is the option E, right? Next one is this question. In the kinetic study of a chemical reaction, the slopes are drawn at different times in the plots of the concentration of reactants versus the time. The magnitude of the slope with the increase of the time, how is that gonna change? So for any reaction that is A to P that is taking place with the due course of time, what is gonna happen? The concentration of the A, it decreases. Concentration of A, it decreases with the time. If you make a plot of this, that is for the concentration versus the time plot, concentration versus the time plot, we measure is the slopes of it. Slope, what does it represents? It represents the change that is taking place. Slope represents the change. So as the initial concentration of reactant, it is decreasing with the due course of time. So the magnitude of the slope, it is also decreasing, which means that if a plot is drawn for the concentration versus the time for the reactants, the magnitude of the slope with the increase of time, it is gonna decreases. That is the option C you will be having it. Okay. Next one we are having is this question. It says a photochemical decomposition of HI, it takes place with the following mechanism. It is given to us. Considering the hydrogen and the iodine atoms, they are the intermediates. The rate of removal of HI. So here the reactions that are given to us is HI plus the H nu. This is of intensity IA. This is giving you the H plus the I. So here the rate, which is the of the HI removal, we can write it as d by dt of the HI. It will be equal to the intensity only, right? Next in this next reaction is hydrogen plus the HI. This is giving us the hydrogen plus the I. This is with the rate constant K1. So in this case, d by dt of the HI, this will be equal to the K1 times the H into the HI. So overall rate of the removal of the HI, it will be minus of d by dt of the HI. This will be equal to the IA plus of the K1 times the H into the HI, right? So now here you see the final expression that we are getting here. The hydrogen is present, which is my intermediate. So we have to somehow eliminate this from this expression. So for this we will be applying the SSA over the H concentration. So we will be applying the this side we can do it steady state approximation. On the H we have to apply it. So consider all the reactions where the H species is involved. The first one we are having is this one. This is of intensity IA, giving you the H plus the I. So here if you see d by dt of the H, here it is getting being formed, so a positive sign is placed. Rate of this, it will be equal to the IA. In the second step, which is H plus the HI, giving you the K1 plus the with the rate constant K1 giving you the H2 plus the I. So for this one again, minus of d by dt of the H will be equal to K1 times the H into the HI of it. These are the two reactions only where the H species is being involved. So SSA has to be applied, which means d by dt of the H, it will be equal to 0. That is, combining these two we are having is IA minus of the K1 times the H into the HI. This is equal to the 0, right? So from this we can find the concentration of H, which will be IA upon the K1 times the HI. This is what the concentration of H we are getting it. So substitute this into the expression so that you can get the rate of removal of this HI. This will be minus of d by dt of HI is equal to the IA plus the K1 times the HI into the concentration of the H, which is IA upon the K1 times the HI, right? So this K1 times the HI from the numerator and denominator, this will get cancelled out. We are having the sum as IA plus of the IA, which will be equal to the 2 times this IA, right? So this is how the rate of removal of the HI will be, that is 2 times the IA. That means the option C, it becomes the correct answer in this, right? Next one we are having is this question. It says in an enzyme catalyzed reaction, the mechanism of which is shown to us. K2 is this much, E0 value is given, the magnitude of the maximum velocity, which means the value of R max is being asked, and the turnover number. Turnover number is nothing, it is the K2 value. Okay, so with the Michael, using the Michael-Menten kinetics are these two values we have to tell them. So the turnover number, it is nothing but the K2, its value is already given to us. So that means this value, it is gonna be 3.42 into 10 raised to the power of 4. So from this only you can eliminate you can eliminate the options. Here you see in the first and in the second the values are 3.42 into 10 raised to the power of 4. But in C and D, if I see, it is some powers they have changed it, which means directly these two options can be eliminated from here, which means our answer is gonna be from the A or the B only. Okay, so now let us find the value of the R max. For the enzyme catalyzed reaction, we have R max is equal to the, okay, so rate is equal to the R is R max into the S upon the Km plus of the S. Okay, and R max value we have to just find it out, that is equal to K2 times the E naught of it. K2 is given to us as 3.42 into 10 raised to the power of 4. E naught value is 1 into 10 raised to the power of minus of 2. So this becomes your 3.42 into 10 raised to the power of 2. Units will be mole per decimeter cube per second. This is gonna be the R max value. So from the A and B you can find this out. That is in the option A you are having this power. So option A becomes the correct answer for this one. Right? Next is this question we are having. The Arrhenius equation for two of the chemical reactions K1 is equal to this and K2 is this. If the condition is given that E1 is greater than the E2 at a given temperature, which of the conditions is true? So rate constant K1 is A1 times the e raised to the power of minus of the EA1, E1 only it is given, E1 upon the RT, and rate constant K2 is A2 into e raised to the power of minus of E2 upon the RT. Take the ratios of these two, K1 by the K2, it will be equal to A1 times e raised to the power of minus of E1 by the RT, and this is A2 times e raised to the power of minus of E2 upon the RT of it. Right? This we can write it as K1 by the K2. It will be equal to A1 by the A2 into e raised to the power of minus of the E1 plus of the E2 upon the RT of it. This is what we can take it. So now it is given to us. So or we can say it is E2 minus of the E1. In that way also we can write it. It will be E2 minus of the E1 upon the RT. Now the given condition we are having is that is E1 is greater than that of the E2. E1 is greater than the E2. That means this magnitude, which is E2 minus of E1, this you are gonna get is a negative value. So here it will become K1 by the K2 will be equal to A1 upon the A2 into e raised to some negative power you are having it. Right? So this this ratio A1 by the A2 is multiplied with some negative value. That means a smaller value it is getting being multiplied. So overall K1 by the K2 that we are gonna get, it will be a smaller value, because with some smaller value this whole is getting being multiplied. So from here we can get is that A1 by the A2 it's gonna be greater than the K1 by the K2. So this condition you will be getting. So that is given to us in the option A. It is given that A1 by A2 is greater than the ratio of the K1 by the K2. I hope it's clear. The next one we are having is this question. So this is from your CSIR December exam conducted in the year 2017. Before this were the June exams. So it says for a sequence of a consecutive reactions, that is A to I with the rate constant K1 and I to P with the rate constant K2, the concentration of I would be by steady state approximation. So the reactions here it is A to the I and I to the P. It is with the rate constant K1. It is with the rate constant K2. So now SSA has to be applied in this intermediate I, because it is getting being formed in the one of the reaction, that is A to I, and in the second reaction, which is I to P, it is getting being consumed in this. Okay, so here the SSA you can apply it over here. So in the first reaction I is getting being formed, so di by the dt, it will be equal to the K1 times the A, and in the second reaction it will be minus of d by dt of I. This is equal to K2 times the I concentration. Now SSA means the net rate of formation of the I is 0, which means d by dt of this I, it will be equal to the 0. So combining these two we get is d by dt of I. This will be equal to K1 times the A minus of the K2 times the I's concentration. This is equal to the 0. So K1 by K1 times the A. This is equal to K2 times the I. So from here the I value we will be getting it as K1 times the A upon the K2. So this is the I value you are getting it, K1 by K2 into the A. That is the option 4. It becomes the correct answer for this. Right? Next is this question. The slope and intercept obtained from the 1 by R against the 1 by substrate concentration of an enzyme catalyzed reaction are this and this. The Michael-Menten constant for the reaction is Km value we have to find it out. For the enzyme catalyzed reaction, rate is equal to R max into the S upon the Km plus of the S. 1 by R, it will be equal to Km upon the R max into the 1 by S plus of the S upon the R max into the S. This S and S gets cancelled out. So this will be equal to Km upon the R max into the S plus of the 1 by R max. So if we are having a plot for the 1 by R versus the 1 by S, that is Y is equal to the mx plus of the c, right? So here the slope value we are having it as Km upon the R max that is equal to 300, and the other one, that is 1 by R max. This will be equal to 2 into the 10 raised to the power of 5, because these values are given to us, slope and intercept values. So from here we have to find the Km value. So we can say that Km into the 1 by R max value, which is 2 into 10 raised to the power of 5, this is equal to 300. So Km will be equal to 300 upon 2 into the 10 raised to the power of 5 of it. So it will become 150, or 150 into 10 raised to the power of minus of 5, or 15 into 10 raised to the power of minus of 4, or 1.5 into 10 raised to the power of minus of 3 molar. This is the Km value that we will be having, right? So that means the correct answer, it becomes the option 4 in this case, right? Next is this question. Reaction between A and B is carried out for a different initial concentrations and the corresponding half-life times. So this time the data is for the half-life and not the rate expressions as given to us. So A and B. So rate, it will be dependent upon the concentration of the A raised to power of some stoichiometry, and B raised to the power of the beta. We will be having this alpha and beta determined experimentally. Now for the nth order T half value, we are having it is 2 raised to the power of n minus 1 minus of the 1 upon the n minus of 1 into the rate constant k into a naught raised to the power of n minus of 1. So we can say that T half value, it is inversely proportional to the a naught raised to the power of n minus of 1. So now we have to find the order with respect to the A and with respect to the B. So for this one we are using is the ratio variation method. Which means the concentration of one of the reactant species we will be keeping the constant, and for the other one we are gonna vary it. Ratio variation method. So with respect to the A, if you have to find it out, so for that B's concentration we will be keeping to be the constant. So choose the data in such a manner. So B's concentration is constant in these two expressions, right? So corresponding T half values are also known to us. So T half 1 upon the T half at the second concentration of A. This will be initial concentration of A, first one, upon the initial concentration of the A at the second concentration raised to the power of n minus of 1. So T half 1, we can say it is 60 upon the 30, it is equal to, so when the initial when the T half value is 60, the initial concentration it is 10, so that comes in the denominator. When the T half value it is 30, the initial concentration of A it is 20, so that comes over here, raised to the power of n minus of 1. So this will be equal to 2 over here you will be having. So this becomes 2 raised to the power of 1. This is equal to 2 raised to the power of n minus 1. So 1 is equal to n minus 1. So n value is equal to 2, which means order with respect to the A that we are having it as 2. Okay. In the similar way for the B, we can find it out. For the B, it's gonna be, now that we have to choose it, that A's concentration, it remains to be the constant. These two datas you are having it, where this A's concentration it is kept constant, B concentration it is varying, corresponding T half values are also given to us, which means 60 upon the 60, this is equal to 20 upon the 10 raised to the power of n minus of 1. So this becomes equal to the unity, which is equal to 2 raised to the power of n minus of 1, which implies that my 2 raised to the power of 0, it will be equal to 2 raised to the power of n minus 1. So n value we are getting here is the 1, which means order with respect to the B we are getting it as 1. Okay, so overall rate value that we will be having it will be proportional to A's concentration square and B's concentration raised to the power of 1 of it, right? So that means A to B, that is the option third one, it becomes the correct one, right? Next is This question you are having, it says the plot of a rate constant versus the ionic strength for the reaction. This is from your primary salt effect. Primary salt effect. According to this, we have is the log of the K naught. Log of K is equal to the log of K naught plus of the 2a times the ZA ZB, where ZA and ZB are the charges present upon these ionic species into the ionic strength root, which will be there, right? So now the ions which are present is A plus 2 and B minus 1, which means the ZA into the ZB term that we are having, it will be plus 2 and the minus of 1, which is coming out to be a minus of 2. So this is the negative value we are having it. Okay, so the expression that we were having, if we rearrange it, log of k minus of the log of k naught, this is equal to 2a times this ZA ZB into the root of ionic strength. So this is log of the k upon the k naught, this is equal to 2a times the ZA ZB into the root of ionic strength. Compare it with the straight line equation. This becomes y is equal to the mx, right? C value, it is 0 over here. So the slope value that we are getting it is 2a times the ZA ZB, and this thing it is coming out to be the negative, which means the slope value here it is negative, right? Because this we have got it minus of the 2 we have got it. So overall minus of the 4a, which means the negative slope value we are getting. So that from the given curves, if you see first, second, third and fourth, the fourth is the one, if you see a plot for the log of the k versus the ionic strength versus the root of the ionic strength, you are getting a negative slope value. This is minus of the f. So that means the fourth is the correct curve for the given aqueous solution. So fourth becomes the correct answer, right? Next is this one. So this is from your 2018 June exam. The elementary steps of a reaction are as follows. If steady state approximation is applicable to the C, then the rate of the product formation in the reaction is. So here you see, here the equilibrium step it is given. In one of the previous year questions we did similar to it. There it was mentioned that this equilibrium step it was the fast one, and this one it was mentioned that this was the slow step. There the equilibrium, that is equilibrium approximation, can be applied, but here it is not mentioned that this equilibrium is fast, so we cannot apply the equilibrium approximation over here. What we can just apply is the steady state approximation. Okay, so firstly the rate of the reaction in this case, it is gonna be equal to K2 times the C's concentration raised to the power of 2 of it, because if it is not mentioned that it is the slowest step, the final step in which the product formation is taking place is gonna determine the rate of the reaction, right? So rate is this one. Now C, it is an intermediate. C is the intermediate, so we have to apply the SSA on it. So include all the reactions where this C component is being involved. So first one is A plus B is in equilibrium with the 2C rate constant K1, K inverse. You can break this. That will be A plus B giving us the 2C with the rate constant K1. Here the C formation we are having. So 1 by 2 d by dt of the C's concentration, it will be K1 times the A into the B's concentration, right? And the other one we are having 2C is giving us A plus of the B. This is with the rate constant K inverse. So minus of 1 by 2 dC by the dt, it is equal to K inverse of the C square, right? So here now one more reaction it is there, which is involving 2C, it is giving you the D with the rate constant K2. So minus of 1 by 2 dC by the dt, it will be equal to K2 times the C square. So these are all the terms where the C component was involved. So combine all of this and find the value of d by dt of the C, which we will be getting it as 2 times the K1 A into the B, right, minus of the 2 K inverse of the C square and minus of the 2 K2 times the C square. This is what you will be getting it as dC by the dt. So now this has to be equated to the 0 to find the value of the C component. So we have got is dC by the dt. This was equal to 2k1 times the A plus of B, A into the B, minus of the 2k inverse of the C square, minus of the 2k2 times the C square. This is equal to 0, which implies 2 times the k1 A into the B. This is equal to 2 times the k1 plus of the 2k2 times the C square. So from here the C square concentration we will be getting it as 2k1 A into the B upon the 2 times the k inverse plus of the k2 of it. So 2 gets cancelled out. It is equal to k1 times the A into the B upon the k inverse plus of the k2 of it. This is the C's concentration. So now substitute this into the rate expression. So rate will be equal to k2 times the C square it was. So substitute this, it will become k1 into the k2 into the A into the B upon the k inverse plus of the k2. So you are seeing that the rate value, it is proportional to the concentration A and the B1. So the correct answer it becomes, this is what was asked, that the rate of product formation it is proportional to A and B. There no powers were included. So option A it becomes the correct answer. Right. Next is this question. For the enzyme substrate, the slope and intercept for the 1 by r versus 1 by s is this 10 raised to the power of minus of 2 and 10 to the power of 2 respectively. E naught value is given and the k1 k inverse by the k2 ratio is given. The value of the k1 is close to. So Michael-Menten constant rate, we are enzyme catalyzed reaction, the rate value we have it, that is R max into the S upon the Km plus of the S. So 1 by R, this will be equal to K max, Km upon the R max into the 1 by S plus of the 1 by R max. The slope value, which is Km upon the R max, this is equal to 10 raised to the power of minus of 2 and 1 by R max. This is equal to 10 raised to the power of 2 of it. So from here Km value we can find it out. Km into the 10 raised to the power of 2, it is equal to 10 raised to the power of minus of 2, which implies Km value will be 10 raised to the power of minus of 4. Now Km, it is defined as the ratios of the rate constants in which ES substrate is getting being deformed to that of the rate constant in which it is getting being formed. So here if you see in this reaction, which is E plus of S giving us the ES with the rate constant K1, in this it is getting being formed, its deformation is taking place in the K inverse and ES is getting being converted to the product P. This is with the rate constant K2. So in K inverse and K2 it is getting being deformed. So K inverse plus of the K2, right, and it was formed in the rate constant K1. This is equal to 10 raised to the power of minus of 4, right. So we have been given the ratio of this K inverse and K2. K inverse upon the K2 is 1000. So we can say K inverse is 1000 times the K2. So you can use this relation 1000 times the K2 plus of the K2 upon the K inverse. This is equal to 10 raised to the power of minus of 4, right. So we are seeing it over here is that it becomes 1001 times the K2 upon the 10 raised to the power of minus of 4. This is equal to the K1. K2 value we have, K2 value we needed. So for that we are having the R max value. From that we can find it out. So we had was 1 by R max is equal to 10 raised to the power of 2. So R max is nothing, it is K2 into the E naught, which is 10 raised to the power of 2 of it. So from here K2 value it will be 1 by E naught into the 10 raised to the power of 2 of it. E naught concentration value it is given to us. It is 10 raised to the power of minus of 6. 10 raised to the power of minus of 6 into 10 raised to the power of 2, which becomes 10 raised to the power of minus of 4 in the denominator. Numerator it will become 10 raised to the power of 4 of it. So now this K2 value we can substitute in this expression so that we can get the K1 value. So we were having K1 value, it was 1001 times the K2 value upon the 10 raised to the power of minus of 4, right? So 1001 into 10 raised to the power of 4 into upon the 10 raised to the power of minus of 4 is the K1, which you see it becomes 10 raised to the power of 8. Consider this as 1000 only, so it approximately becomes 10 raised to the power of 11. So K1 answer, K1 rate constant value will be 1 into 10 raised to the power of 11. That is option A, it will become the correct answer. Okay. Next is this question. It says the difference between the activation energies for the reverse and the forward step of the reversible reaction is this much. Okay. If the pre-exponential factor of the forward reaction is double that of the reverse reaction at the same temperature, the equilibrium constant. So the rate constant for the forward reaction, it will be A times of the forward reaction into E raised to the power of minus of the EA of this activation energy of the forward reaction upon the RT of it, and the rate constant for the backward reaction, it will be the exponential factor of the backward reaction into E raised to the power of minus of activation energy of the backward reaction upon the RT of it. Now K equilibrium that we defined, it is the ratios of the rate constant of the forward to that of the backward reaction. That will be equal to A forward E raised to the power of minus of E forward upon the RT upon the A times A of the backward E raised to the power of minus of the EAB upon the RT of it, right? So A forward, its condition is given, the pre-exponential factor of the forward reaction is double that of the reverse reaction, which means A of the forward reaction is 2 times the AB value, that is pre-exponential factor of the backward direction. So we can substitute this relation upon the EB into E raised to the power of, overall it will become activation energy of the backward minus that of the forward direction upon the RT, right? This thing it is becoming, so this pre-exponential terms it will get cancelled, so E raised to the power of minus of the activation energy of the backward minus that of plus of this is there minus of the activation energy of the forward direction upon the RT. Now the given is the difference between the activation energies of the reverse and the forward, which means activation energy of the backward direction minus that of the forward direction. It is 9.21 RT. 212 RT. Substitute this value. This becomes 2 times E raised to the power of 9.212 upon RT upon the RT. So this RT and RT is getting being cancelled out. So the answer is 2 times E raised to the power of 9.212. So just solve this and get your answer. So on solving this, we get the answer as 200. It is equal to 20033. This is the answer, which we can say it is approximately 2 into 10 raised to the power of 4 of it, right? That means the correct answer it becomes the option B in this case, right? Next is this one. So this begins your December 2018 exam. The first question it says for a second order reaction, the straight line among the following plots is, for a second order reaction you have the integrated expression as 1 by A minus of 1 by A naught is equal to KT. So 1 by A it will be 1 by A naught plus of the KT. If you have a plot for 1 by A versus the time, Y is equal to the mx plus of the C. Okay, for the plot of 1 by A versus the time, we are getting as a straight line. So 1 by x versus the time give us the correct straight line for the second order. Option B, it becomes the correct one. Right. Next is this. The activation energy of a reaction, it reduces by 12 kilocalories per mole in the presence of the enzyme. So firstly, the reaction, it was carried like this. It is the plot. If you see, we are having, this is for the energy versus the reaction progress. So some reaction you are doing it. This is the reactants with some activation energy. Suppose it is being converted into the product P. This is the one. So this is, suppose this will be the activation energy, it will be required in the absence of the catalyst. Here no catalyst, you have used it. Now the same reaction, it is carried out but in the presence of catalyst. So reaction activation energy, it will be lowered. So path followed is the different. Now here the activation energy will be this much now. Right? This is the activation energy in the presence of the catalyst. Okay, so this is what is given, that the activation energy, it reduces by 12 kilocalories per mole in the presence of the enzyme. Enzyme is your biological catalyst only. Okay, so this much decrease that we are having. So you can see this difference is for the activation energy in the absence of the catalyst and the activation energy in the presence of the catalyst. This how much decrease we are getting, that is of the 12 kilocalories per mole. Okay, this is temperature at 300 Kelvin, assuming the pseudo first order kinetics factor by which the rate has increased. So we have to find the rate constant values that will be in the presence of the catalyst upon the absence. This we had to find it out. Okay, so let us do this now. So the rate constant in the absence of the catalyst, it will be A times A pre-exponential vector e raised to the power of minus of the activation energies in the absence upon the RT. Right? The rate constant in the presence of the catalyst, it is gonna be pre-exponential factor A. This A, it is gonna remain because reaction we are doing is the same only. E raised to the power of minus of EA in the presence upon the RT. So A value we have kept to be the same reaction we are doing it, just it is the catalyst role is coming into the play, and catalyst only affects the activation energy and not any other things. So the ratios of these two now, rate constant in the presence to that in the absence, it will become E raised to the power of minus of activation energy in the presence upon the RT upon the E raised to the power of minus of activation energy in the absence upon the RT. E and E I have already cancelled it out. That becomes equal to E raised to the power of activation energy in the absence minus of the activation energy in the presence of the catalyst upon the RT. This is what we are having, and this value, it is already known to us, that is the difference between these two, it is 12 kilocalories per mole of it. This value it is, let us just substitute this. So it will be E raised to the power of 12 kilo, so 1000 it is coming, calorie per mole of it, upon the R, which will be 2 calories per mole per Kelvin, into the temperature, which they have taken it as 300 Kelvin. So this will be 300. So with this per Kelvin, this Kelvin will get cancelled out. Calories per mole and calories per mole unit, it get cancelled out. It becomes E raised to the power of 12,000 upon, this is 600. So this becomes 20. So e raised to the power of 20 we are getting it, right? So this on solving you will be getting the value as 5 into 10 raised to the power of 8. So the answer will be the option D in this case. So it will be approximately 4.98 you will be having into 10 raised to the power of 8. That is, you can write it as approximately 5 into 10 raised to the power of 8 of it. Okay. Next is this question you are having. It says the key uni is the effective first order rate constant for the following unimolecular reaction. Okay, mechanism of which is given. The slope and intercept value of 1 by the uni versus 1 by m is this and this. The value of the k inverse upon the k2. So what we do is in the unimolecular reaction, you have these two, A and A, these combined with the rate constant K1 and the backward rate constant is K inverse. This gives you the activated complex A star plus of the A. And in the second step, this A star, it gets converted into the product P. This is with the rate constant K2 that thing happens. Now instead of the one of this A, they have taken is just this M term has been used. So this is for your unimolecular reaction, this mechanism. Now for this, the rate expression, the rate constant value that we write it, rate expression we are having it as K1 into the K2 into the A square upon the K inverse of A plus of the K2. So this is the rate expression that we get it for this unimolecular reaction, right? So for this one, the actual reaction that is taking place is A is getting being converted into the product P, right? So for this, the observed rate constant, suppose it is K dash. So for this, rate will be equal to the K dash into the concentration of A, right? So same reaction, it is just there. It has first one, it has taken place in number of steps, and this we are showing is the overall rate constant, overall reaction and the corresponding rate. Both of these are the rate expressions, so can be equated. So we will be getting it K1 into the K2 into the A square upon the K inverse of the A plus of the K2. This is equal to your K dash times the A. So this A and A will get cancelled out. So observed rate constant value K dash, it will be equal to K1 into the K2 into the A upon the K inverse of A plus the K2, right? So now this plot is for the 1 by the K UNI. UNI is just the effective rate constant or the observed rate constant. So we will be having 1 by K dash versus the M. I told instead of the M we are having is this A term. In the mechanism it is the A term which is involved. So 1 by K dash versus the 1 by A plot. So this becomes K inverse of A upon the K1 into the K2 into the A plus of the K2 times the K1 into the K2 into the A. So you see this A and A, it's getting being cancelled out. It will be equal to K inverse upon the K1 into the K2 plus of this K2 and K2 is getting being cancelled out. 1 by the K1 times the A. This is equal to 1 by K dash. Right. So from here, if I see this plot is for y is equal to mx. This is y mx plus of the c. So the slope value we are getting it is 1 by the k1, and that value it is given to us as 4 into 10 raised to the power of 6 of it. So the slope value is 1 by k1, that is given to us as 4 into 10 raised to the power of 6, and the intercept value we are having is k inverse upon the k1 into the k2, that is given to us as 8 into 10 raised to the power of 11 of it, right? So we have to find is the ratio of this k inverse to that of the k2. So use this k1 1 by k1 value. So k inverse upon the k2 into the 1 by k1, that is this value, 4 into 10 raised to the power of 6. This is equal to your 8 into 10 raised to the power of 11. So this becomes 2, and K1 by the K2 value, it's gonna be 10 raised to the power of 5 of it. So this is gonna be the ratio between these two, right? So the answer it says is 1 into 10 raised to the power of, or some factor, 2 into 10 raised to the power of 5 we are having it. So the answer becomes the option A in this case, right? So this is the first time this plot for the 1 by K versus the 1 by A we are having for the unimolecular reaction. So far the plots just mostly have been asked us from the Lineweaver-Burke plot. From the unimolecular reaction, this is the first time that has been asked. So it becomes your important question, and the possibility is there that this type of the concept, it can be repeated in our exams. Okay. Next is this question. It says the decomposition mechanism of the ozone is this much. A condition is given, the order of reaction with respect to the ozone. So for this reaction, which is O3, is in equilibrium with the O2 plus the O. The rate constant is K1. This is K inverse. This is O3 plus the O with the rate constant K2 is giving us 2O2. So the rate of reaction, it will be equal to K2 into the O3 into the O, right? Now here this O that is formed during the reaction and it is consumed during the course of reaction. So this is my intermediate. We have to eliminate this. So we can apply the SSA over it. Steady state approximation on the nascent oxygen, we have to find it out. So for this d by dt of the O, we have to find this out. This will be equal to the 0. So in the first reaction, it is O3. I'm breaking all the reactions, giving us O2 plus the O. This is with the rate constant K1. So d by dt of the O, it will be equal to K1 times the O3 of it. The other reaction we are having it, which is O2 plus the O, giving us the O3. So minus of the d by dt of the O, this will be equal to, this is with the rate constant K inverse times the O2 into the O, right? And in the next step, that is O3 plus the O, giving us the 2O2. So from this one, minus of the d by dt of the O, this will be equal to K2 times the O3 into the O, right? So combine all of this d by dt, so you can get it d by dt of the O, it will be equal to K1 times the O3 minus of the K inverse of the O2 into the O minus of the K2 times the O3 into the O. This is equal to the 0. So from here the O's concentration we can find it out. That will be K1 times the O3, K1 times the O3 upon the K inverse of the O2 plus of the K2 times this O3. This is what is we are getting the O's concentration. Now a condition is given to us which says K inverse of O2, it is less as compared to the K2 O3. So use this condition now, that my K2 O3, it is much greater than the K inverse of the O2. So nascent oxygen concentration, it will become K1 times the O3 upon the K2 times the O3. This it will become. So this and this gets cancelled out. It becomes K1 by the K2, right? So you can substitute this into the final rate expression that we were having was this one. So the rate will become, rate was K2 times the O3 into the O. So K2 times the O3 into the O's concentration that we have got it as K1 by the K2. So K2 gets cancelled out. So overall rate it becomes K1 times the O3. So this is gonna be the final rate. So the question it was asking the order with respect to the ozone, so it's ozone raised to the power of 1. So this becomes the order unity. So B is the correct answer in this case. Okay. So this was the last question that was to be discussed in this part. So thank you so much for watching. I hope all the questions that we have discussed so far are clear to you. If you still have doubted any of the questions that I have discussed in be it in this part or the previous parts, that you can ask me in the comment section. I'll surely reply to that. But if you have understood the concepts, then make sure you like the video and don't forget to subscribe to the channel because many more videos are on the way, and share it with your friends as well. Okay, so thank you so much for this one. I'll be meeting you in the next part now with some new questions. Okay.